Welcome to Voltage Equation. Today, we will explore one of the fundamental principles of electromagnetism, Faraday's law. We will break down the theory behind this law, explaining how a changing magnetic field can induce an electric current in a circuit. Then, we will dive into some calculations to understand how we can quantify this electromagnetic induction in different situations. Finally, we will bring theory to practice with an exciting experiment where you can see Faraday's law in action. We will use simple materials to demonstrate how a moving magnet can generate electricity, thus confirming the concepts we have discussed. Join us on this fascinating journey through the world of electromagnetism and discover the magic behind Faraday's law. In 1831, Faraday, a self-taught science enthusiast, discovered a principle that would revolutionize our understanding of electromagnetism and lay the foundation for many modern technologies we consider indispensable today. This principle, known as Faraday's law of electromagnetic induction, describes how a change in the magnetic field can induce an electric current in a circuit. In other words, Faraday discovered how to convert magnetic energy into electrical energy. Faraday's law describes how an electric current is generated by a changing magnetic field. It states that a variation in the magnetic flux through a closed circuit induces an electromotive force, EMF, in the circuit. The formula is as follows. The first variable refers to the induced electromotive force, and the second part is the rate of change of the magnetic flux. Imagine an inductor and a magnet. If you move the magnet in and out of the ring, the magnetic field changes, inducing an electric current in the wire. The negative sign in the formula indicates that the induced current opposes the change in the original magnetic flux, according to Lenz's law. To apply Faraday's law in an experiment with 2 meters of wire, we will calculate the number of turns of the coil, the cross-sectional area, and the rate of change of the magnetic flux. The general formula for Faraday's law is as follows, where the first part is the induced voltage and N refers to the number of turns in the coil. By substituting the values into the formula and performing the corresponding calculations, we can determine that the induced voltage would be approximately 10.048 millivolts. With 32 turns, you should be able to detect this voltage with a multimeter. Now, let's put what we've learned to the test. Here I have a coil and a magnet. My goal is to measure the induced electric current when we move the magnet inside the coil. As you can see on the multimeter, the current changes with the movement of the magnet. This is a clear example of Faraday's law in action. Remember that using only 2 meters of magnet wire for the Faraday experiment can limit the number of turns you can make in the coil, which in turn will reduce the induced voltage. Lastly, here are some tips for the experiment. 1. The faster you move the magnet through the coil, the greater the induced voltage will be. 2. Make sure the magnet passes as close as possible to the core of the coil. 3. Inserting an iron core can increase the inductance and, consequently, the induced voltage. Faraday's law is fundamental in the generation of the electricity we use every day. From wind turbines to nuclear power plants, all leverage this principle to generate energy. For example, in a hydroelectric power plant, the moving water spins turbines connected to generators. These generators use Faraday's law to convert mechanical energy into electrical energy. Despite lacking formal education in mathematics, Faraday conducted some of the most important experiments in the history of physics. His legacy lives on in every generator and electric motor we use today. What other experiments would you like to see on our channel? Leave us your comments. If you enjoyed the video, don't forget to like and subscribe for more content like this. Until next time,